Hey everyone, Morgan here. So we're going to take a more in-depth look today at the concept of polyprotic acids. All right. Now, let's look at H2SO4, which is a strong acid to begin with. H2SO4 can react with water. It dissociates. We get H3O plus and HSO4 minus. This is going to be a stepwise dissociation. And the Ka for this reaction would be called Ka1. Now the HSO4 minus ion can react with water and can produce H3O plus and SO4 2 minus, and it would have a Ka2. Now if we look here, Ka1 in this table is just listed as large. It's a big number. Full dissociation. None of the H2SO4 is left. Now, that is not 100% true, but it's true enough for the math that we're going to be doing. The very, very complicated idea of some ion pairing, and that can come into play. Now, Ka2 is 1.2 times 10 to the negative second. This second dissociation is almost a strong acid. And in fact, I know some teachers that do call it a strong acid, although it isn't. It dissociates a lot. Okay? Now, what we need to take into account here is that for any polyprotic, Ka1 will be greater than Ka2, which would be greater than Ka3 if it exists, etc., etc. And typically, what we can say is that Ka1 divided by Ka2 is going to be about 10 to the fifth. So the first dissociation is about 10,000 times stronger. Okay? So, I'm sorry, that would be 100,000. I am so sorry about that. So you can get a lot more hydrogen or hydronium ion, whatever you want to call it, off of the first dissociation than off of the second. Now, I've got some different acids listed here. Carbonic acid, 10 to the negative 7th, 10 to the negative 11th. That actually matches. Difference about 10 to the 5th. Phosphoric acid, 10 to the negative 3rd, 10 to the negative 8th, 10 to the negative 13th. Pretty darn close to that pattern. Okay. So each successive dissociation is going to be a little bit weaker. And what that tells us is that sometimes we really only care about the first dissociation. So for H2CO3, 0.10 molar, let's look at this first one. H2CO3 plus H2O gives me H3O plus and HCO3 minus. I'm going to do an ice box here, nothing special really. 0.10, ignore that. 0, 0, minus X, plus X, plus X. 0.10 minus X and X are those totals. Okay? Now, my Ka, number 1 is going to equal X squared over 0.10 minus X. That's 4.3 times 10 to the negative 7th. I got that out of the table up above. Okay, so doing a little bit of math here, X ends up equaling 2.1 times 10 to the negative 4th. And the 5% rule is good. It is ionized less than 5%. Okay, about 0.2% total. All right, so that equals the H plus concentration after one dissociation. Now how about a second dissociation? HCO3 minus plus H2O gives us H3O plus and CO3 2 minus. I'm going to make an icebox. Now here's where things are different. The initial concentration of the HCO3 minus is 2.1 times 10 to the negative fourth. I calculated that up here. The initial concentration of the H3O plus will be the same. And there'll be no carbonate. Minus x plus x plus x. I have 2.1 times 10 to the negative fourth minus x. 2.1 times 10 to the negative fourth plus x and x. So when I plug this into Ka2, this is 2.1 times 10 to the negative fourth plus x times x over 2.1 times 10 to the negative fourth minus x. And all of this equals, my second k is 5.6 times 10 to the negative 11th. All right, so now, I can most definitely approximate this. So the plus x and the minus x are gone. Which means then this cancels this, or that x simply equals 5.6 times 10 to the negative 11. So that's how much more hydronium ion is produced. And it's negligible. I mean, even if I add them together, 2.1 times 10 to the negative fourth plus 5.6 times 10 to the negative 11 equals 2.1 times 10 to the negative fourth. So this is actually a really nice example also of Le Chatelier's principle and what we can call the common ion effect also. Because we already have a relatively large amount of H3O plus, the amount that can dissociate off of the HCO3 minus is drastically reduced. It really goes down a lot. Okay? Now, if maybe I was starting out with a species like NaHCO3 rather than H2CO3, I'd get more dissociation off of that HCO3 minus at that point. Okay? So for this weak acid, that second dissociation is just negligible. It's really not going to matter. Okay, so now, how about for H2SO4? This is a very different ballgame. Now, for the first dissociation, H2SO4 plus water gives us H3O plus and HSO4 minus. Basically, this is 0.10 molar, which turns into this being 0.10 and that being 0.10. Okay, there you go. Boom. Okay, that's how much HSO4 minus we have. Now that's a borderline weak acid. HSO4 minus plus H2O is going to give us H3O plus and SO4 2 minus. Ka2 equals 0.012, or 1.2 times 10 to the negative second. Okay? Now, we're going to do a proper icebox. 0.10, ignore. This will be 0.10 also. That'll be 0. Minus x plus x plus x. 0.10 minus x. 0.10 plus x, and x. Now, this is mathematically going to be more challenging. I have 0.10 plus x multiplied by x divided by 0.10 minus x equal to 0.012. And that is not something that I can approximate. So I am going to end up actually with the quadratic equation. So what I have on this side is 0.10 plus x multiplied by x equals 0.012 multiplied by 0.10 minus x. So this times this, okay, gives me 0.10x plus x squared equals, this times this is 0.0012 minus 0.012x. Now, when I go to group-like terms, and I bring these over to the other side, I get x squared plus 0.112x, okay, minus 0.0012 equals 0. This and this added together to give me the 0.112x. Okay? Now, what I'm going to do is run that through a quadratic solver in a calculator, which I have here. Program, quadratics number 6. So A in this case was 1. B in this case was 0.112. And C was negative 0.0012. And what was, did I do something wrong here? Let me try that again. Program, quadratic. A is 1. B is 0.112. C is negative 0.0012. Boom. So 0.00985 and a negative number I don't care about. So x in this case equals 0.00985. Now, this is actually going to make a difference. So up here, if I calculated the pH, it would equal the negative log of 0.10, and that would equal 1.00. Now here, if I take my 0.10 plus 0.00985 as the total H plus concentration, that gives me 0.10985. More. And the pH equals the negative log of 0.10985, and that equals 0.96. And on a logarithmic scale, that is a substantial difference. So what I'm seeing here is that for H2SO4, which is a strong acid, both dissociations matter. The second dissociation is almost a strong acid. But when I was looking back at H2CO3, the carbonic acid, the second dissociation gave so little hydrogen ion that it wasn't going to change anything. Now, is common ion effect happening here? Absolutely. So if I was dealing with something like NaHSO4, the dissociation of that HSO4 minus would give you a lot more H plus than this one does. Okay, so they have not actually asked for a polyprotic on the AP Chem exam in the past. It's not part of the list. Definitely fair game on Chem Olympiad. But I think it's good to look at these more challenging situations, because if you can deal with them, then you're going to be able to deal with just about anything. Okay, that's all for these 2 pages. This is Morgan, signing off. Thanks for tuning in.